Hi everyone, and welcome to yet another virtual chemistry lesson. In this video, I thought we should spend some time learning how to balance some more complicated redox reaction formulae with the help of oxidation numbers. Quite often we see reactions that are quite complicated, involving strong reducing and oxidizing agents. For example, if we were to mix potassium permanganate and glycerol, they will after a while start to react and burn with a nice purple flame. And balancing that reaction straight up and thinking of what is the actual reaction formula isn't that straightforward. So what we're going to go through is a method of how we can balance reaction formula using oxidation numbers. Before you attempt this, I'd like you to have some prior knowledge about chemistry. I'd like you to have know some fundamental theory concerning ionic compounds. I'd like you to understand the concepts of reduction and oxidation, at least the basics. You should also know the basics concerning oxidation numbers for atoms in substances and compounds. Right. So oxidation numbers, they give us an approximation of the number of electrons that are lost by substances through the process of oxidation, and the number of electrons that are gained by substances through the process of reduction. And oxidation can never occur without a reduction, and vice versa. And the number of electrons that are lost through oxidation will always equal the number of electrons taken up through reduction. This is a fact that we then can use to balance redox reaction formulae. So, let's start simple. When zinc reacts with oxygen gas, the following reaction occurs. Zinc oxide is being formed. What we're going to do now is that we're going to balance this reaction using oxidation numbers. You may know, hopefully, how to balance this reaction without oxidation numbers, but we'll illustrate the principle and then we'll apply it to something more complicated. Step 1, using this method, is to write out the oxidation numbers. Elements in their natural state, they have oxidation numbers of 0, zinc and oxygen gas. They're in their elemental states, so they have the oxidation number of 0. And for ions within ionic compounds, the oxidation number will correspond to their charge. And since you know that oxygen always forms 2-, then zinc is likely to be, or it's bound to be 2+ in this. Note that zinc goes from an oxidation number of 0 in its elemental form to an oxidation number of +2 in its ionic form. An increase in oxidation number corresponds to an oxidation, so we know that zinc will oxidize. Oxygen, it starts with the oxidation number of 0 and ends up with -2, that's a decrease. Therefore, that corresponds to a reduction. Alright, now let's split up this reaction into half equations. The oxidation looks like this. Zinc turns into zinc 2+. In order to do that, it must also give away 2 electrons. Otherwise, we have an equal proportion of protons and electrons within zinc and the charges cancel out. So only by donating or losing electrons can it gain a positive charge. For the reduction half equation, well, oxygen goes from its elemental form to oxide ions. In order to do so, for example, first and foremost, we need to have 2 oxide ions for every oxygen molecule. And then we need to add 2 electrons. 4. 2 per oxide ion being formed. So in total 4 electrons. Note that we need to have the same number of electrons lost in the oxidation as are taken up or gained by the reduction. So we need to multiply everything in the first half equation by 2 to get 4 electrons up here, because we have 4 electrons down here. If you do that, you will have this. So 2 zinc turns into 2 zinc 2+ ions, and 4 electrons are lost. perfect for every oxygen molecule. Now we combine the half equations into a complete redox reaction. Then you take everything before the arrows and combine, like so. And then you write a new arrow, and then you take everything that was behind the arrows before, like so. And it looks like this. And now you can see that on both sides of the arrow we have the same thing, that is 4 electrons. And if something is before, the same number before and after, we cancel it out. If it's identical before and after a chemical reaction, we cancel it out, like so. And then we tidy up if we have access to animation. Alright, so let's clean up this formula, make it a little bit prettier. We add states of matter, and then we combine ions into ionic compounds where appropriate. In this case, a metal reacting with a gas will result in a solid ionic compound being formed. So this becomes the following formula. 2 zinc atoms in the solid state reacts with an oxygen molecule in the gaseous state to form 2 zinc oxide. Alright, so this seems needlessly complicated maybe. To go into this, you already know how to balance a reaction formulae this way, so why do you need to know this? Some reaction formulae are more complicated than we have looked at so far. For example, reactions where we need to deal with acidic or basic conditions. Always try and balance a reaction formulae the old-fashioned way, and if that doesn't work, then you can use the oxidation number method. However, in order to do this for even more complicated versions of formulae, we need a more specific strategy, and that will be outlined here. This seems rather daunting. It's 7 steps, and one of the steps is divided into sub-steps. We're going to go through all of these with an example, and then we're gonna balance a complicated redox reaction formula using this strategy right here. For example, whether or not we have acidic or basic conditions will influence how we balance the equation. But I'd like you at this step to pause the video and spend some time writing this down. Then we're going to go through it when you're ready, so then you're free to unpause the video. So, let us balance the following reaction formula. When iron ions, 2+, reacts with the permanganate ion, iron 3+ ions are formed together with manganese 2+. And this is a reaction that, in this example, takes place in acidic conditions. All right. The first step was to assign oxidation numbers to each atom and identify what's oxidized and what's reduced. So, first and foremost, what is the oxidation number for manganese in permanganate? Well, the permanganate ion, it's an ion, a polyatomic ion, consisting of a manganese atom and 4 oxygen atoms. Alright, so we can split it up this way, as shown here in the bottom. So 1 manganese and 4 oxygen, and the total charge is -1. The oxidation number then for manganese, it's a transition metal. It's not obvious what it is straight up. However, oxygen always has -2 within compounds as a general rule. So we can add that up, and you know that the sum of all the oxidation numbers equals the charge of the polyatomic ion. This we can write as an equation like this, or like this: x plus 4 times -2 equals -1. You solve that, and then you will find that x is +7. And then we can easily write out the rest of the oxidation numbers above this main formula here. For ions, it's the same as the charge. Oxygens, each of them will have -2, and the manganese will have +7. Iron goes from an oxidation number of +2 to +3. That's an increase, and therefore it corresponds to an oxidation. Manganese goes from +7 to +2. That corresponds to a decrease in oxidation number, and therefore a reduction. All right, since we know what's oxidized and what's reduced, we can split this up into half equations, and they're written here. Iron 2 plus turns into iron 3 plus, and the permanganate ion is going to turn into manganese ions 2 plus. All right. Then we balance these half equations with the respect of the number of atoms on each side of the arrow, like we usually done before, right? So let's start with everything except for hydrogens and oxygen. And it's done. We have 1 iron here, and we have 1 iron here in the oxidation. We have 1 manganese here, and we have 1 manganese here. So that's balanced. Now we're going to have to balance all of the oxygens with water molecules. In the first formula here, we have no oxygen atoms, so we're done. But here we have 4 oxygen atoms. So we're going to have to balance those up with 4 water molecules. Each water molecule carries 1 oxygen atom, so you need the same number of water molecules as you have oxygens on the other side. And then you simplify the remaining hydrogens with an H+. This is a simplification of oxonium ions in an acidic solution, a water solution, but it's a good approximation to use this because it will simplify things a little bit. And it's a convention used. We're going to need 8 of these H+ for every, to balance up 4 water over here, because 4 times 2 is 8, like so. All right. Now, if this reaction occurs in acidic solution, we continue to step 4 of our strategy. And in the information of the exercise, it said that the reaction indeed occurs in acidic conditions. So we go on to step 4. So now let's balance each half equation with respect to charges by adding electrons where appropriate. So here I like to count the total number of charges before and after the arrow. For the oxidation half equation, we have a total charge of 2 plus before and +3 afterwards. Okay? And for the reduction, we have 8 positive and 1 negative charge. Sum that up, it's going to be a total of a charge of +7. Here you have 1 with a 2 plus, and then the water molecules are neutral. They have no charge. This will be 2 plus here. The oxidation half equation can easily be balanced by just adding 1 additional electron. Then it will change into 2 plus here, because we sort of balance the charges, and we have 2 plus here. But for the reduction, we're going to need quite a few more electrons. We have to add 5 electrons here to bring this +7 down to +2. If we do that, we will have the same number of total charges on both sides. All right. Now we need to balance them against each other so they have the same number of electrons. Because as you recall, the number of electrons lost must equal the number of electrons gained. So in this oxidation half equation, we have 1 electron lost, and in this reduction, we have 5 electrons gained. All right. We need to multiply the oxidation half equation by 5 to bring this number of electrons up to the number we have down here. Then we get this. And then we can add them together. And then we can cancel out electrons if we have the same number on both sides of the arrow. So let's do that. Let's take everything before the arrows. like we did before in the simpler exercise. Everything before the arrows, then you make a new arrow and you take everything after as well. We take from the oxidation half equation and we take from the reduction half equation. Like so, and that's a very long reaction formula, isn't it? Okay, but we can simplify this a little bit. As you can see, we have 5 electrons on both sides of the arrow, so we can remove them to simplify the expression. And then we have this equation, which is a little bit simpler. Right. The last thing to do is to make a table and just sum up all the information we have. Number of atoms before and after the arrow and charges before and after the arrow to see if we have the same. We have 5 iron atoms before and 5 afterwards. That seems to fit. We have 8 hydrogen. Yep. And 8 hydrogen. Agreed. 1 manganese before and after. We have 4 oxygens. Here they're stuck to the permanganate ion. Here they're in water molecules. And then we need to count the charges in total here. So here we have 5 times 2 plus. That corresponds to 10 plus. We add an additional 8 plus 1 charges, so we're up to 18. And then minus 1 from the permanganate ion, so we're down to plus 17 here. On this side, we have 5 times 3 plus, that's 15, plus 2 plus, which is plus 17. And if your table looks like this when you're done, you've done a good job balancing a redox reaction, like using the oxidation number method. You're done. I hope you learned something today, and I will see you in a later video.